So, okay, class. So we're about to discuss now some basic principles on how to determine whether the matrix is positive, definite, or not, and what is the relation of such property into solving optimization procedures later, no? When we deal with numerical problems. So what's covered by this presentation is enumerated here. We have the test to check whether the matrix is positive and definite. What is the quadratic form and how it can be used to check the positive definiteness of such a matrix. Okay. And also we will be looking into the geometric interpretation for us to be able to appreciate. No? So I want you to appreciate always the principles class, because this is only the way on how we can motivate ourselves to proceed and go on to the more difficult situations. Also, how to make a matrix positive definite if it is not symmetric. Okay. So, but before we do the checking, I'd like to tell you that uh, all the matrices that is covered with stress and strain analysis, okay, belongs to this, okay, type of matrix which is positive and definite. Okay, why is it called the positive and definite matrix? So we will look into it as we go along. So first we have to check, in order to determine whether it is a positive definite matrix, we have to have some procedures on how to deal with it. And we have a lot of procedures to learn, and some of them are already very familiar to us. Okay, so the matrix, in order to be positive definite, has to be symmetric. Okay, so we know that stress matrix or stress tensors, okay, so you can see the relationship between continuum mechanics now and numerical methods. That's why indicial notation is very important in programming. Okay, so a stress tensor is always symmetric. Therefore, conclusion, it is a positive definite matrix. And we have proven it in continuum mechanics that the stress tensor is symmetric. Remember, sigma ij is equal to sigma ji. Okay? All eigenvalues of a matrix are positive. So have to check the eigenvalue solution. So in your advanced mathematics and in your structural dynamics, I already taught you on how to deal with eigenvalue problems, but in numerical analysis, not yet. So maybe later, rather in continuum mechanics later, we will be doing some eigenvalue determination. Okay, so this is yet to be tackled. On the third note, all subdeterminants are also positives. Okay, when you say subdeterminants, we are looking into the submatrices which are uh, leading minors. Okay, leading minors. So these are the terms that you need to know when you read it. What is a lead minor of the matrix? Okay, if you have a 3 by 3 matrix here, like this, what are the lead minors or the sub matrices? Sub means a part of the matrix. So the lead minors normally are those which involves the submatrices that are the including the whole matrix, no, the main the regular matrix, and the submatrices involving a diagonal at the upper left. Okay, so this is a sub matrix which is a lead minor of the matrix. Okay, it has the diagonal on the upper left. This is also a lead minor. It has a diagonal on the upper left. Okay, can you see the lead minors? It has the diagonal. This is also, this small scalar quantity is, it can be considered a submatrix of the whole matrix, which has the lead minor on the upper left as the diagonal. So you get the determinant of each submatrices and check if it is a positive value in order to conclude whether it is a positive definite matrix. Okay, so you get now the definition of what a positive definite matrix is on the context of this tree. Okay, this fourth, I really don't have not tested it, but I have read it in many references, pero hindi ko pa na-test ito, that if the pivots are positive, and what are the pivots? These are simply, again, the basis for the Gaussian elimination technique that we term as pivot. But I don't use this simply because I have not tested it for most of the matrix involved. But I can see it on some references. If the pivots are positive, meaning to say they are greater than 0 numbers, then your matrix is positive definite. But I don't like you to check each and every 1 to 4 here, because there's a better way on how to ensure that the matrix is positive and definite by simply testing the quadratic form of the matrix. Okay, what we are going to test is we only need this single form of the matrix and check whether it is a positive definite matrix. And sometimes, pag nakakita na tayo ng word na quadratic, the tendency is we think of it as a very difficult procedure, no? But it has nothing to do with a quadratic equation. The reason why it's called quadratic form, I will tell you later. So what is a quadratic form and how it can be used to check positive definiteness? First, we, of course, define what a quadratic form is, and this is the main formula used by Shaw Nakagome on what a quadratic form is all about. And this is a purely mathematical statement, and it is written on a mathematical format that a quadratic form is a condition such that the x value is an element of R, okay, matrix M by 1, and A is also an element of R. R are, of course, real numbers, which is a matrix M by M. Okay, so there is what? Congruence in the value, or so the size of the matrix M, or the vector M here, and the vector X here, and the matrix A here, which has an M by M size. Okay? So, dapat merong congruence dito. Or else, you cannot check. Why? Because the checking is done using the X transpose AX operation. And this is a dot product. In mathematics, automatic, when you're dealing with matrix and vectors, you are dealing with dot products. So it's simply a dot product of X transpose A and X. Okay? So the X are the X vectors, the vectors of unknown. If you have a 6 equation with 6 unknowns, then X is 6 elements. And your matrix will be a 6 by 6 matrix. And if we do the dot product of this X transpose AX, we will lead to a scalar value because of contraction. Okay? So you can contract this. This will collapse. So you will have an m by 1 there. And then you can also contract m here. It will collapse. And you will have a 1 by 1 matrix in this form. And this is what you call a scalar in tensorial mechanics. Okay? So, if I know tensors, I know matrix, I just get this from a good source. I read it. There's no problem with me understanding it. Why? Because the language is not different from what I understand. But if you don't know about matrix vectors and tensors, etc. properties, you will find this a very very hard to present, because this is not my own lecture. I told you, I just want to share it to you because I find it very easy, and I find it very important for you to understand before we proceed with the conjugate gradient technique. Okay, so this is a quadratic form. It has nothing to do with a quadratic equation. The reason why this is called a quadratic form is because you are multiplying a vector matrix and the transpose of the vector all at once, and you will yield to a scalar value here. Okay, so the description of being quadratic has nothing to do with a quadratic equation. Okay, let's write now the quadratic form in terms of what? Explicit notation, expanded notation, or the expanded form. Okay, so this is now your row vector, okay, multiplied by a matrix, and then this is your column vector. So I hope you know how to multiply it. Okay, if manually you are given the exam to multiply it without the use of a computer, you just get your calculator and multiply this row to this. Okay, you will have the first element, then multiply this with this, you will get the second element, and then you multiply this with this, and so on and so forth until you get finally the mth element here. Okay, which is no longer x. I mean, let's say xm, you place here maybe a b element there. Okay, b1 to bm there. Of course, the size of this is m, and the size of this is m. They will be compatible now. If I multiply this with this, I get what? A summation series, which will lead to a constant. So this is initial format. But if you will do it in terms of matrix multiplication, it's easier, and I have proven that in your continuum mechanics. Okay, so again, this is a scalar quantity because this is what? a summation operation collapsing into a zero index, which gives you a scalar quantity. And this is not difficult, just like the author is telling us right now. Okay? Now, to check if this is positive and definite, upon computing, you just look if it is a positive value and if it is a real value. It is defined, and therefore, you have no problems on it. And if you will look back into what I told you a while ago on stress tensor, what I told you is that a stress tensor is always a positive definite matrix. Always. Why? Because it already has passed the test of symmetry. It will have an eigenvalue since this will give you a solution to equations. A positive definite matrix, to extend it to linear algebra, will give you a solution vector. And therefore, it has an inverse. Imagine a system of equation without an inverse. You cannot get anything out of it. Okay? But as I've told you, this simple test can be summarized into one test only, which is to look into the quadratic form and check whether the value is positive and definite, so that you can conclude with confidence that your matrix is positive definite. Then you can proceed with the rest of the uh, procedure, especially looking into an optimization procedure like the conjugate gradient procedure. Imagine doing something, class, doing something, let's say, doing an optimization procedure, and then without knowing that the procedure will simply fail up after you have tried so many times. If you know na failure yung gagawin mo ba, gagawin mo pa? Di na, di ba? Of course, sasabihin mo, you have to try. You try. There's no harm in trying. But if it is a sure failure, will you proceed with it? So this is the case of uh, of uh, uh, assuring yourself that there is a solution to the problem. And you can do it by simply checking the property of being positive and definite. Okay? Okay. So to proceed, what happens if this is 0? What happens if the value here is 0? Huh? Is it positive and definite then? Of course, if the value is 0, meaning to say your solution is trivial. Your solution will yield to only a solution that is not significant. That's the meaning of a 0 value. And if it is negative, then your solution will diverge. Okay? And you can make use of some subcategories of positive definiteness in this form. If it is positive definite, or sorry, if it is greater than 0, meaning to say it is positive and definite. I'm talking, of course, of the quadratic form, this one. Okay? If it is greater or equal to 0, then it is maybe positive semi-definite. And if it is less than 0, it is a negative definite. There's a danger of divergence. There's a danger of triviality here. But here you are assured of a solution. Okay, so let's get the the meaning of it. I like this analogy of Dr. Shaw on this. The geometric interpretation of positive definiteness is actually uh, can be thought of on the concept of or on the understanding of its meaning in a geometric perspective. Okay, so this is very significant on machine learning optimization. Machine learning is only programming, of course. If you the word that they use here, this is simply programs, computer program. Okay, so this is because the positive definiteness could tell us about some geometric plane of the matrix, and this is the geometric interpretation. So let's not uh, discuss on what Dr. Shaw has presented here, but rather jump directly to what the figure is all about, the interpretation. And this is the interpretation of the plane upon which the bowl shape, okay, representation of the geometric shape of the quadratic form is, if you try to use the eigenvalue uh, method of finding the equivalent surface equation of such, then you can interpret it in this form. This is a positive definite interpretation of the matrix in the quadratic form presented above is. And what is the relationship of this in terms of solution? The solution is actually the lowest point upon which this surface, okay, is described. Imagine if you have a ball, no, and you let the ball roll within the inner surface of this bowl. What will happen? The tendency of that ball is to what? To be converging into the lowest position. So you are assured of a solution. Your only problem is what optimization technique will you do in order for the ball to yield this position fast. Okay, did you get the point there? If it is positive definite. This has something to do now with the gradient technique. Why? Because the gradient technique will determine the slope upon which you will start the ball rolling. Will I place the ball here on top? Will I place it somewhere in the middle? Wherein all of these positions have different slope upon which the ball can start rolling, which will represent your trial solution vector. If your trial solution is very close to this point, then you will converge faster. Okay? So that's how optimization is related to the positivity and definiteness of the matrix. Or sorry, of the quadratic form of the matrix. Now, let's look into a saddle shape. The saddle shape is actually a positive but a semi-definite matrix. Sometimes you will be lucky enough to let the ball stay in this position, which is what? It's neither the minimum or the maximum value of the gradient involved here. That's why it's very difficult. What if you start the trial solution here? It cannot go up, but it will fall down and yield to divergence. Okay? So it's semi-definite because it has something to do how lucky you are to place or to let the ball fall into the correct answer, which is this point here on the saddle. And of course, we have the third one, which I missed, no? I missed to cut and paste here, is the reverse of this disc into a dome shape. Imagine you have a dome shape figure here, like this, okay? Wherein the maximum point is somewhere here, maximum minimum problem. So the gradient here is a maximum, meaning to say the derivative of the dependent variable here. If this is xy, this must be z, or this, but this is xy for a right-handed system. This is z, a function of xy here. So the partial derivative of z with respect to x and the partial derivative with z with respect to y is a zero slope, meaning to say you are maximizing the value of your z there. So do you think it is a stable condition to put a ball here? Only a slight error will yield the ball rolling down this slope and finally diverging into an erroneous result. In fact, if you started an initial value here, it will not go up because the tendency for this ball is to move down. Unless you exert a force that will trigger the ball to be placed on that position, but that's not a way on optimizing your resources when it comes to programming. Okay, so these are now the three geometric interpretation, and if you will look into this example of a simple matrix here in terms of a two-dimensional coordinate, you will just take a look on how it was done. You have now the x1, x2 here. This is your matrix. This is the x uh, transpose. This is the A, and this is X. So I do the multiplication, and of course you must have a point upon which your function must be evaluated. Okay, so you can do some substitution later. So question, if your function of x1, x2 is greater than 0 for all x, then it is now a positive definite matrix. Except, of course, with a very trivial case wherein your x1 and x2 equals 0, this can be evaluated to 0. Okay? So, how do you do the derivative? Okay, the partial derivative, the gradient that we will be dealing with next time when we study now the technique itself. Also, okay, so you just take the partial derivative of this function, which was derived from the quadratic form. Okay, and then of course, partial means you are differentiating it one at a time with respect to the first and the second variable, and then come up with this equation. Okay, if you get the second derivative, you will have yielded, of course, a constant here, because from a quadratic form, you reduce it to a linear form, and then you reduce it to a constant form, etc. Okay, what is this again? In our continuum mechanics, this is just a del operator. Okay, a del dot f. Okay, what's a del? A del is just a partial derivative symbol, okay, with respect to x's. Okay, so this is just a del squared of f. So you can now relate on how things are done if the language you are looking into is familiar. Just like going to a place wherein the dialect or the language is different, there's no way you can come up with a better understanding on how to deal with it. Okay, so the rest of these mathematical formulations are just exercises on what you can do when the matrix is positive definite. It has no relation, direct relation on the principle of optimization on the conjugate gradient problem. But I'd like to share to you this short lecture by Dr. Shaw on how to deal with positive definite, how to check, and how to convert a matrix which is not a symmetric to a symmetric matrix. Or sorry, yes, to a positive or to a quadratic form to check whether it is positive definite matrix. And that is only by multiplying the matrix with its transpose to make it symmetric and square. Okay? So this is a question on how or what, how to check the quadratic form of an unsymmetric matrix. Of unsymmetric matrix. Okay, so this is how to do it, no? So if the matrix A is not symmetric, then you first get the A transpose A and go with the quadratic form. Originally, the quadratic form is X transpose AX. This time, it will be X transpose of this value A transpose A. And then, by using a property of matrix multiplication, we can actually distribute or mix up this operation into this. AX transpose AX is simply the square of this value. Okay? You can manipulate this and you can manipulate this. What does it mean? You multiply the dot product between A and X and then get the transpose. I hope you know how to get the transpose of a matrix. And then multiply it with the value or dotting it with the value of AX will give you an AX squared. It's just like getting the value of this and then squaring it. So this is an identity that you can test using MathCAD. This is fast, no? You can just type the A matrix and the X vector and do it in MathCAD. You can just get the value of this. And this is now a scalar. Okay? This is now a scalar. And if comparing this, you get now what? The property of positivity and definiteness when it is greater than 0. Okay? So, to summarize, this is the summary. Test to check positive definiteness. We used rule number 5, no? The quadratic form, just to get rid of all the types of tests, which are sometimes what? Only a part of what the fifth test is all about. Okay, so you might as well do the quadratic form, which is already a complete test to be assured of positive and definiteness of the matrix. And of course, this is the conclusion. If the quadratic form is greater, then it is positive definite. If it is greater and equal to 0, it is positive semi-definite. And if it is less than 0, then it's a negative definite matrix. Okay, positive bowl shape, positive definite. Uh, Saddle shape, it's positive semi-definite. And the dome shape is actually a negative definite. Okay, I just maybe miss the conclusion here because I just copy it and then cut and edit some of the things that are not really relevant to my presentation. So thank you very much for listening. I hope this will give you a good preparation on when we go to the conjugate gradient method.